We're going to continue our work with complex numbers, looking at the roots of complex numbers. In this section, we want to find the nth root. So this involves solving equations such as x to the sixth minus 1 equals 0. Now, fortunately, this one factors, and so we can factor it and then use the quadratic formula and that kind of thing. And this one's not too bad. However, x to the sixth plus 1 equal to 0 would be very difficult algebraically because it doesn't factor very well. Right. Let's look at the calculator though, because the calculator would solve x to the sixth plus 1 equals 0. Right, notice the C solve, that means we want complex solve. And so we're scrolling over so that you can see all of the solutions. And there are 6 of them. It's kind of hard to follow. And so basically we have 6 imaginary solutions. To algebraically solve this equation, we would need more knowledge of how to find complex solutions. Now, that's what we're going to find because we have a definition here. The complex number u equal to a plus bi is an nth root of the complex number z when z equals u to the n, which equals a plus bi to the n. So we're wanting a z here. So to find these roots, the first thing we want to do is put z into our trigonometric form. We'll use trigonometric form all the way. It has exactly n distinct nth roots, and they are given by that formula. The nth roots of z all have the same magnitude, the nth root of r, so they all lie on a circle of radius nth root of r with center at the origin. The nth roots will be equally spaced around the circle. I've pointed out 3, and there would be n minus 3 more of them. So let's find all the 6th roots of 1 in trigonometric form, then convert to algebraic form. First, write 1 in trigonometric form. 1 is 1 plus 0i, so a equals 1, b equals 0. The point 1, 0 is on the positive x-axis, so theta equals 0. Therefore, z equals 1 times cosine 0 plus I sine 0. But the nth root formula, n equals 6. So r equals 1, theta equals 0. The zeros have this form down here. Do you see the 2 pi k coming in? And so if we crank out all of them, you can stop the video if you want to and determine where the pi over 3 came from, the 2 pi over 3, pi, 4 pi over 3, 5 pi over 3, and so forth, so that we could find all 6 roots of 1. Now, this is significant, and we're going to do some by hand here in a few seconds. Please notice how they are equally spaced around the circle. Now, so same answers as doing it algebraically, but a lot easier. Those were called the nth roots of unity. The process works even when not finding the roots of unity. Let's try a few. We're going to try a few. For example, we could use the formula to find the 6th roots of 64. So let's start with finding some roots of unity and then go to finding the nth roots of 64. So we want to find the 5th roots of negative 1. We'll use radians. So x to the 5th equals minus 1 plus 0i. So a is minus 1, b is 0. Inverse tangent of 0 over minus 1 is pi. So theta equals pi, and r is equal to 1. So we will need k equal to 0, 1, 2, 3, and 4. z sub k then will be the fifth root of 1 times the cosine of pi plus 2 pi k over 5 plus I times the sine of pi plus 2 pi k over 5. So we'll start with k equaling 0. When k equals 0, notice how we've plugged in, then used our calculator, and there's the first fifth root of unity. Now, we take a k equal to 1. Well, pi plus 2 pi is 3 pi over 5, so that you can see how we're getting those angles. So we have the second fifth root of unity. Now k is 2, and so pi plus 4 pi is 5 pi, and that one's easy. K equals 3, z3 will be the cosine of 7 pi, and you now know how we're getting those, so we use our calculator there. And do you notice that this is very much like the first the k equal 1 root, and except the signs are different. What do you want to suppose that this one's going to look like that first fifth root of infinity with, excuse me, of minus 1 with a different sign? Yeah, it's always going to work that way. There is a relationship because they are symmetrically placed around the unit circle. So we're now going to try to find the sixth roots of 64. X to the 6 equals 64, and so r is equal to 2. Inverse tangent of 0 over 4 is 0, and so because we are over 64, I'm sorry, so theta is 0. So here's our z sub k that we always start with, but we want k now to be 0 through 5. So we'll start here with our first root of 64, and we get 2. Now, if k equals 1, then we get our second one, so we have 2 times the cosine, and notice we went up there, 0 plus 2 pi over 6 is pi over 3, so we get 1 plus the square root of 3i. We go ahead, do the same thing for all of these, right? Do the same thing. The 0 plus 2 pi k, when k is 2, we had 4 pi k, over 6, or 2 pi over 3. Do you notice here the relationship when k equals 1 and k equals 2? And look at the relationship between 0 and 3. Remember, we have symmetry relative to the going around the circle, and so therefore these are all just have the same numbers, just different signs. Right? And our last one here for k equal to 5, we get 2 times a half minus the square root of 3 over 2. And so you notice 4 of those look a lot alike, and then we have the 2 and the minus 2.